Some font issue, fine. Where we have it. No, I don't anything. So we'll discuss discrete Fourier transform, which is used to calculate a spectrum, just like for continuous signals. We discussed that there is a spectrum, there is a time representation of a function. So essentially, that means you can, you know, uh, trade one for another, such as, for example, for rectangular shaped signals, we can calculate uh, the spectrum, and we already discussed how exactly we are doing that by calculating the scalar product between your signal and well, base function you are trying to discover the contribution for. So let's say again, for examples, we have a rectangular closed shape signal. Then you have supposedly this harmonic, which you consider is most important in this shape. Then you try to find exactly how much does it contribute to the shape of signal by finding this product between this line and this line. However, if we speak about continuous signals, then that transform is going to be calculated as follows, like an integral, starting at minus infinity, ending at plus infinity, this signal of t, which is your function, green line, multiplied by a harmonic, which in our case is, let's say, sine wave of some base frequency, omega capital T by dt. So that's what you need to solve in order to find how much exactly that coefficient would be. Yes? Now, this is, of course, difficult to do, especially for signal for which you might not even know how exactly to write it in this formula. For rectangular shaped signal, it's actually easy. Yes, so this signal S of t is, uh, well, either plus u or zero, depending on what time range we are discussing. Usually we speak about one period, say then start from zero. Here we have one period t, here we have t by half. Yes, so in range from 0 to t by half, we can say that your signal is plus u, and otherwise it's 0. Yes, so t more than. So there actually is a formula, and in this case it's going to be easy integral, yes, because you are going to have a constant here, you need to integrate just a sine wave, and that is a minus cosine, I believe, yes. So still you have to do calculus, still you have to calculate this integral, put in some limits, specific numbers, and all that stuff. Now in digital world it's going to be much easier, although essentially the same stuff. So that's why we will start from it to actually get a good understanding of what exactly and how that happens. And in general, this kind of transform called Fourier transform, yes, which connects your signal shape with its spectrum represented by these harmonics. Yeah, so it actually is possible to calculate from a spectrum a signal, just like from a signal a spectrum. So we did both in our exercises already. So, and essentially that means it works in both directions. And it's commonly used for different purposes, such as spectrum analyzers. Yes, when you have some radio signal received, and let's say you try to see and analyze it, or maybe somehow intercept it or do some stuff with that, you need an equipment to actually see what frequency band that signal is using. Or let's say a speech processing. Yes, whenever we say we want to call with our mobile phone maybe you just don't realize, but your, well, in my speech of human, yes, is actually represented as this kind of a autoregression model signal, which spectrum lies within frequency band from 300 for 3400 hertz. That's acoustic properties of our speech uh, organs, yes, that acts as these resonators, creating resonances at specific frequencies. And turns out that for each letter, like A, there is its own picture. For letter B, this picture is different, but more or less ideally seems to be the same. So the compression here allows you, well, Fourier transform allows you to achieve some compression by saying, okay, most of the sounds have only like 3 peaks, yes, or how they call formants, yes, and you need to know what its frequency is, f1, and what is its amplitude. So that's essentially just 6 numbers, and you can reconstruct from these 6 numbers back your original sound with even ability to recognize the person who is saying that sound, um, to accordingly transmit it in much more compressed way. Or say, if you don't want to keep the voice, but just an information, if you want to, somehow make this sound unrecognizable, that is also an option with the Fourier transform. You can analyze which of these 3, for example, specifically is responsible for your tone and which is responsible for information part. So you can easily make this still to be understand what it is saying without understanding who is saying that anymore, like this robotic machine voice, yes, and stuff like that. So that's speech processing. It can be used. Similarly, we can use that also for image processing, especially different kind of filters, improvements to image, etc., etc. Or go even further to object recognition, like you have some handwritten text, scanned it, and you want, to optically recognize it by running some OCR algorithm. So that also depends a lot on Fourier transform. Nowadays, we do a lot of machine learning, true, but even in machine learning, you still can use Fourier transform as one of the steps. So that's actually quite useful. Now, what we need to say about it is that normally in a computer, we don't use something called discrete Fourier transform. We use something called fast Fourier transform, FFT, of which you might even already have heard. So it is the same discrete Fourier transform, except that that is just an, how they say it, an implementation of this algorithm. Yes, you can have an algorithm and have multiple versions of how you implement it, like, I don't know, some sorting algorithm or whatever else, yes. Some of them might be faster and more efficient than others. So Fourier transform is the algorithm, whereas fast Fourier transform is its implementation, very fast and very efficient, so very popular because of that, but it gives numerically exactly the same result as that less efficient direct approach of discrete Fourier transform would give. That's also what we can compare. And we can use that as well for filtering purposes, well, such as image processing filters, for example, yes, when you want to blur some fragments of image or sharpen them, vice versa. So that's basically about it as well. Now let's speak a little bit about the family of Fourier transforms, because there is actually multiple versions depending on what exactly is your signal. So option number 1, let's consider that your signal is now continuous and non-periodic. Yes, so some pulse that starts and ends and doesn't repeat over. In that case, we use something called integral Fourier transform that is most generic and most universal thing, yes. That's exactly the formula I was writing before, signal multiplied by the base function. Well, let's use a complex one, omega t by dt minus infinity plus infinity, yes? So that is the integral formula of integral Fourier transform. That's actually working for any signal. Now, it's the thing that once we start speaking about that your signal is somewhat specific, like periodic, for example, or discrete, then you have some, you know, how you can say, improvements to this formula to make it easier for you to work with. For example, if we speak about Fourier series, yes, that's a specific case of Fourier transform when your signal is periodic, not non-periodic, but still is continuous. Now your signal repeats over and over and over, but in that case, your Fourier series are now represented by this, uh, well, it's a signal equal to the summation. Now the summation is not an integral, it's a limited sum, yes, of your components, let's call them C complex, multiplied by K omega capital T, like so. Now, in order to find the C component, however, you still have to calculate integral. Yes, that's it. Signal of T multiplied by e power. So here we have plus, here we have minus. So at least one of these two formulas, because for previous formula also signal was an integral. So now one of these formulas is a summation, not an integral, which is much easier to work with. Well, that is because your spectrum is now finite number of samples, like so, and not a continuous line like here, which consists of infinite number of points. Okay, next we go to the discrete series, yes? So now we have signal read by samples. It does not exist between these samples, so we speak about discrete signal and non-periodic discrete signal. For that, we use something called discrete Fourier series. Now that is actually seems like to be the case when we will want to use this Fourier transform to calculate spectrum of some signal that we have. Say you have accumulated some numbers and you want to calculate for them. However, it's not called discrete Fourier transform as we heard about, as we discussed right now, but instead discrete Fourier transform is calculated for this case when your signal is discrete and periodic. Now, there is no real contradiction in that because normally signals we consider are not infinitely long. They have starting point and ending point just like so, and nothing prevents you from saying, let's assume that before this signal started and after it started, I am going to periodically reproduce it. Yes, in that case, you kind of make it periodical in your head, but in reality, it's just a fragment, just one period of what you actually have, and you don't know for certain if it would go like that or not because it's unended. Yes, so it happened. There is nothing else in that signal. It's just that we assume that it might have, continued like periodical. In that case, this gives you the right to use this discrete Fourier transform, which is represented as a signal, as a finite amount of, well, actually, we'll have formulas right now, like so, yes, as a finite summation. Now, that's very convenient for us because now this xn is not a function anymore, but rather than that, a sequence of numbers like 1, 5, 3, and so on and so on. And adding numbers, well, even multiplied with this weird complex exponential, is very nice and easy, yes, in a computer. Because, well, computer is meant to add or multiply numbers. That's its primary task, yes. Of course, we then, go higher levels and say, okay, adding this and multiplying this is going to make you a filter or a simulation of a physics fluid or whatever else, yes. But under the hood in the computer, there are just regular mathematical operations it's performing, adding, subtracting, multiplying, dividing. And it's good at that also. Yes, so that means we can actually now calculate that in the computer very easily and fast and efficiently, as long as you have some way of giving the computer the signal. Yes, for that we have something called analog to digital converter, ADC. That's exactly doing it. Yes, say you connect some device to your computer, and let's say microphone, for example. Yes, it's recording analog signal, well, not recording, but working on an analog signal, but inside of it, there is also a microchip that converts your analog signal into codes that are then transferred by USB protocol to your computer, and therefore are numbers which you can now, I don't know, see, for example, as the spectrogram, yes, of your message, of your recording. That's what you can do with audio editing tools, for example, yes. Now, what you need to realize that there exists also a similar formula to perform this operation in reverse, like say x small letter of n, that is to find the signal value based on your spectrum. Yes, so that would be summation without 1 divided by n, just summation for k going through 0 to n minus 1 of x capital K multiplied by e power of plus j to p and k versus n. So the only things that change is that this goes away. You also interchange these two, you change places, and you also change the sign to plus. So that is direct transform, that is inverse transform. Yes, and they are also very similar formulas to the point that you can actually use the same algorithm to calculate both of them without the need to write one special algorithm for direct transform, one special for inverse transform. Now that's very convenient also. Now here, let's agree that, as we agreed in the beginning, we will continue calling capital letters as the result of transform, that is the spectrum, that is Z transform, that is Laplace transform, and whatsoever, but it's not a time units, yes? And small letter x small is the time process, yes? Like which changes in time as a sequence of numbers or continuous line or whatever else, yes? So that's a convention that's widely used, involved in literature, in science, everywhere, yes? And that's why we will use that as well. N is number of time sample, and K is number of frequency sample. So that means that for discrete process and discrete Fourier transform, both your signal and spectrums are sample. Yes, so they are discrete. Now you may recall that previously, well, you might be a little bit confused right now about this complex exponential. Although, if we think about it, not really, if you say that a complex exponential can be represented by Euler's formula as a cosine alpha and sin alpha, then that makes perfect sense. Especially considering that what we did in practical exercise previously, when I changed cosines to sines, and you get completely different signal. Actually, most of the signals contain both cosines and both sines, yes, sines. So basically that means if we were to go that way, you would have to have two formulas. One formula where you will calculate cosines to p and k versus n capital, and another formula where you will calculate sines to p and k versus n capital. Now, by using Euler's formula, you can actually combine them into one formula and use it just one. And if you will want to know what is about cosines, then you take a real part of your result. If you want to know specifically what happens to sines, you will take a imaginary part. Now, if your signal only has cosines, then your imaginary parts are always going to be zeros. So that is also taken care of. So this is a universal approach which doesn't matter what exactly you use. Sine waves, cosine waves, both of them actually, yes. So that works regardless. And you still can create, well, describe this by Euler's formula as these two and split that summation into two parts. Yes, so real part, imaginary part. Now those are base functions. These are base complex exponential functions, which we will speak a little bit more further later. But as of now, you can think of it as simply convenient way to combine both cosines and sines into one function so that you don't need to do this job twice, one time for cosines, one time for sines. Yes. Now this formula itself is called a convolution. Yes. Now that describes a convolution between two sequences. One is your signal, and yet another one is a base function. So convolution is actually calculating of the, how it's called, scalar product, yes, how we have called it, but in a digital form. So that means you find the contribution of each harmonic, and there is limited amount of them too. And even more so, if you were to calculate spectrum of discrete process, you would see how it starts to repeat itself, just like we discussed when we talked about sampling, when I demonstrated that rotating wheel, how it changes directions constantly, yes? So that is also observable from the spectrum too. Okay, so now let's consider some example. Here you have some samples. They may have some specific numbers, may not. Well, maybe we have time, yes, so let's also start octave. And just to show you how exactly that works, we'll do more advanced stuff on the practical exercise this Wednesday, but now just some generic demonstration. So let's say now I will have this sequence as, I don't know, 1, 2, 1, 1, 1, 2, 1, 3. For example, this sequence. Of course, it's more accurate than that, but I have kind of rounded it, yes, to an integer. So now I am going to specify this signal as a sequence in octave, like X small letter, like 1, 2, 1, 1, 1, 2, 1, 3. I have now 8 samples, yes. And what I want to do now is to calculate the spectrum of this sequence, yes, as a signal. So that is done step by step, starting from first component, second component, third component, and so forth. For example, if we speak about component with number k equals 0, then you need to calculate the cosine, yes, of 2p and k versus n, where n is changing in range from 0 to n minus 1, and k is 0. So that means your entire cosine, regardless of n, in brackets here has 0. Cosine of 0 is 1. Yes? So here is cosine of 0 with the same samples matching your signal. So what happens now is you take this sample of your signal, multiply it with this sample of cosine. This sample multiplied with this sample of cosine, and so forth. Then you add all 8 of them together into one single number and divide by their count. So effectively, what has happened here is you calculated the average of these samples, right? Because x0 plus x1 plus etc. plus x7 divided by 8 is actually an arithmetic average of this number sequence. That is called the C component, yes, direct current component, the average part of your signal, which is calculated exactly like so, yes. Now you also need to calculate the same for sin of 0. Now sin of 0 is 0, so all of these multiplications will be zeros and adding up into the 0 number. So imaginary part is going to be 0. Now we get k increased to 1. Now you have a cosine of 2pn versus 8, that is p divided by 4n. And here you see one full period of cosine. Yes, full period of cosine sampled at the same time intervals as your signal. You multiply this with this, this with this, this with this, mutually in pairs, yes, add everything together into one number and get this real part. You do the same stuff for sine wave and you get imaginary part. And you go through all of them for k starting from 0 and ending by n minus 1, or maybe not, we'll see, but at least you want to know all of them. The question is, do you really have to calculate all of them considering the symmetry I have discussed? Yes, because what's the point of calculating them again if you already have and you know for certain they will be reflected? So you can calculate half of them and say the other halves are going to be symmetric. So next, k equal 2, you have cosine of 2 periods, yes. So essentially this number k says how many full periods are going to be within this time duration of signal, and you go through all the way up to k equals 7, calculating all cosines and sine waves. Now let's see this as an example. For example, here you can see all of these cosines for every k value. So each row is one case. For example, k equals 0 was 1, 1, 1, 1, 1, 1, 1, as you remember. Yes, that was shown in the k0 scenario here, cosine 0. Now, next one is when k is equal 1. Well, it's actually, no, it's here cosine. Now that is a cosine as it goes from +1 through 0 to -1 through 0 and all again up to +1. That is the full cycle. Now you see that for k equal 2, it repeats faster and faster and faster. But here is an interesting thing now that let's maybe use some marker. Let's say, for example, this k equal 3 and k equal 5. See how these cosines are exactly the same. Just like also k equal 2 is exactly the same as k equals 6. They are just the same base functions. That's called aliasing. If you recall, we discussed about it, that as a bad effect, yes, like you cannot really distinguish from this perspective two cosines with different frequencies, like say cosine of let's say k equal to, yes, 4p and k, no k, 4p n versus n, and cosine of 12pn. Now, if you draw them completely as a line, that would be different. But if we say about samples, then, well, sadly, that's going to be it. Yes, the sample-wise, they are going to be the same. So again, let me just demonstrate that in Octave. Say I want to have some time vector of one period. So that will be from 0 to, with a step 0.01 to double p. Then I display plot of cosine, how I was saying, then 4p versus 8 multiplied by time t. Hold on, and plot of cosine 12 multiplied by p versus 8 multiplied by t. Hold off. So the line-wise, they seem different, yes? But if we were to take 8 samples in this duration, then you would surprisingly see that these samples are the same. Yes, so let's now try to make these samples. That's probably going to be stem, and we need to have them equally. Yes, so length of t is 629. So if we split that into 8, then the step of time is going to be 78. Yes, so then n is going to be starting from 0 with a step of length t versus 8 all the way up to uh, the end. No? No, wait a minute. Wait, but why? It's just enough to have double P versus 8. And I also double, because I know the end point that is double P. I have specified it directly here. Yes, so I know this, and I can put it directly, actually more accurately even. So now we have actually 9 samples. Mm, because I started from 0, so no, but it's fine from 0. Well, it's okay. I'm just going to skip one last sample, say that n is going to be n from 1 to 8 instead, and hold on. But but wait, I need to redraw it again. I didn't specify time. So here we have time cosine, time cosine, hold on, stem n, and cosine of double p n multiplied by either one of these two k's. So that's, let's say 2, for example, versus 8. And hold off. Well, hopefully it matches. And kind of, I suppose, not exactly. Everything needs to be a little bit moved. Well, no, it's not exactly what I hope. But anyway, even without that, we can actually see these points where it's the same. It's here, it's here, it is also here, it is here, 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 and here. That gives you 8 points, I suppose, right? No, 7 actually. Maybe I missed one, not sure. But either way, well, point number 8 would be here at 0, but it wasn't here, yes? So we never reached it. You can see that actually if we see only these samples, then you cannot really say was that blue line on orange ray based only on these samples, yes? That's the problem of aliasing. However, for us in this particular situation, that only means we can calculate this just once and get the same result calculated. So that stands for cosine. If we check what happens to the sine waves at the same time, then you will see very similar pattern. For sine waves, actually, there is slight change. It's with opposite signs. Yes, so if it was plus, now it's minus. If it was minus, now it's plus. Yes, see, the sign has changed. So that means that they are not actually exactly the same. They are complex conjugates to each other, but it's still easy to do because, well, okay, you will not add imaginary part by subtract it, so that still means you only need to effectively calculate 4 of them, and all the others can be mirrored and complex conjugated. So this table shows you these values for sines and cosines. The idea is that now I would give you some numbers, exactly what I was using before, like 1, 2, 3, and so on. And then we would, kind of with sheet of paper calculate. But that's not what we do in the signals theory. That was some other lower courses of the students. So here what we will try to do now is to simply see how we calculate this spectrum-wise. So basically what I want to do is to create the same matrices now, yes. Now I can do this by specifying this as a vector row and this, no, as a vector column and this as a vector, Well, actually, it's the same way. K is column, N is row. So let's try to do that. Clear. Wait, but I wanted to have this signal. So N is going to be a vector row. K is going to be a vector column. So if I now multiply column with a row, not like we usually do, row with a column, I would get a square matrix. So I multiply K with N, like so. Yes, this is the multiplication table, like 7 by 7, 49, and so on, when we were young, well, children basically, and learning this table from head. Yes, we had this on different, notebooks, and so on and so on, try to memorize it. But actually, it's constructed as this matrix product, yes, which might be interesting to know. Okay, anyway, I didn't specifically want this table of multiplications of products, but rather than that, a cosine of double P Kn versus 8. Now, here you have the same numbers. Well, let me just make them format short. I do need some number, format short G, probably. Generic. Okay. 1, 0.7, 0, essentially, minus 0.7, and so on. So you can see only three different numbers actually. 1, 0.7, or 0. And all the others are variations with different signs, almost 0, and so on and so on, yes? So what I have now is my sequence X. So what I want to do now is take the sequence X, the first row of this matrix, yes? So let me call this M. Cosine. Now X. Now I don't put a point because I want to have a matrix product. I want to take this signal X and this as a column, then multiply row with a column and get one single number. That's going to be average. Let's find out actually if this is average or not. So X multiplied by M first row and all columns, yes, transposed, because I want this to be a column. And versus 8 also, I did forget, divided by 8. So the answer is 1.5. If I calculate mean of X, it's also 1.5. So that's actually physically the idea that the C component is the average of the signal, yes? Now, if I do the same stuff for sine waves, let's say this is M matrix cosine. Now I'm going to have a same matrix of sine waves. Sine waves. And calculate it like this. Sine waves. Then that is 0, because sine of 0 and k is 0, yes? So that means all sine points are zeros. Now, I won't go this one line by line, but instead I'm going to say, please do this for the entire matrix right now, like so. So it's automatically going to take this row, and each of them convert to column, row by column, row by column, row by column, to produce you 8 outputs. Just like so. See, it has calculated all of them. Same way I can do with the cosines. And if I add them together, so that would be X capital and starting with the cosines, plus 1i multiplied by sines component. Then I have calculated Fourier transform for all of them. Well, it's not looking smooth, so I'm going to transpose it like so. And here you can see what I was speaking about, that this one and this one are very similar, with one exception. This is plus, this is minus. They're complex conjugates. Just like this one and this one. Well, numerically, these are maybe a little bit different, but this is minus 16, minus 17, so that's 0, essentially, here, and 0 here. Yes? There is only one uncompensated one, which does not have a pair. It's in center, minus 0.5, and at the beginning, which is the average one. Yes? Surprisingly, now I will do the same stuff with a complex exponential with just one line of code. Yes? So I will have my signal x multiplied with a matrix form exponent of minus 1i multiplied by 2p k by n versus 8 transposed. Versus n divided by 8, sorry. And also transposed to match. There you have it. With a complex exponential, I needed to calculate this product only once. I did not have to calculate product for cosine, product for sin, add them together, and so on. Yes, so that's already taken care of inside of this exponential. Yes, so you get this number right away. Now, you can calculate any of them or all of them in a matrix form. That's actually up to you. Now, that is the strong part of this discrete Fourier transform. Now, what about the fast Fourier transform? The fast Fourier transform, as I said, is the same discrete Fourier transform. It calculates the same stuff. Yes, so if now I say run FFT x versus 8, and I do transpose it also, you get exactly the same numbers. Yes, well, actually, it's even more accurate here in 0, yes, than here. So number-wise, discrete Fourier transform here and fast Fourier transform here is the same, because it actually is the same thing. It's fast Fourier transform, just a way to calculate FFT, and it still does so accurately. Now, if we compare them efficiency-wise, then for discrete fast Fourier transform, you have to calculate n square multiplications of complex numbers, which makes sense. Yes? Well, okay, let's switch to slides here. Because here you have n rows and n columns, so there is total of n square of sines, n square of cosines, so that brings you to n square of complex numbers, which cos is the real part and sin is imaginary part of. So that's all the products you have to calculate. But we already have noticed one important thing, actually few important things. First of all, there is absolutely no need to calculate these products again. So we can skip on them, ignore. That brings you already to half of the products to calculate. Second part is that if you look closely, you will notice that actual multiplications are always happening with a very limited number of possible values. So like there is really like around 4 unique multiplications that can be done. So it's actually not that many of them. So that's what fast Fourier transform actually exploits. Yes, this repetition of numbers, because here is 0.7, here is 0.7, here is minus 0.7, and so on. They always repeat. And you need to realize that with this 0.7, you will multiply x1. And here, for when you will calculate for k equal 3, you will already have this calculated by that time. You already calculate this product when you calculate k1. So no need to do that again. Same way for 1. It's just change the sign. You don't have to really multiply with 1, actually, yes, which is a blind approach, what the computer simply do because it's programmed to. Yes, it's not going to check if it's multiplying with 1 or not. So there are ways to improve it. So that brings you to actually having of n versus 2 log 2 of n products instead. So let's say in our case n was 8. That means for DFT you needed to calculate 64 complex multiplications. Now for FFT, that would be 4 multiplied by 3, 12 products. that's 5 times less work to do. And multiplication is more complex operation than adding. Yes, it's taking some time. It's mm, needing some memory and so on and so on. Yes. So in general, it's a good idea if we can reduce this number of multiplication without losing accuracy. That's the main point. We still do the same stuff, but in more optimal way. You can think of it as saving any intermediate results. So whenever you calculate x1 multiplied by 0.7, you recorded it somewhere, and when next time you say, I need to calculate x1 by 0.7, then you say, okay, but I already calculated that. So you go and see in cache, for example, what was that answer, and do not calculate this product again. Same goes for minus. You simply change a sign. Yes. Now, of course, this is well, if you listen to it, it seems like very easy, but we will need some kind of a formal algorithm, some structure to program to do all that stuff for us. It's like easy to say about this table, about idea and all that stuff, but actually it has been done a long time ago already in many efficient ways. There are only two limitations, however, for fast Fourier transform, which are important to notice. First of all, you have to have 8, 16, that would be 64, power of 2, 32, and so on, number of samples. You cannot calculate fast Fourier transform for 1000 samples. You need to have 1024 samples to do so. That is a limitation. Well, not really important one, maybe inconvenient a little bit sometimes, but essentially if you have millions of data, then for you it doesn't matter if you cut them into thousands or 1024s, yes? That's easily avoided. In the worst case scenario, if you just miss some data points, you can always attach some zeros at the end to compensate for that, and it will still work. Yes. So this limitation is just important to remember that FFT actually requires to have a power of 2 as number of samples. Another limitation is that if you speak about FFT, there is no really choice what components you want to calculate and what you do not want to calculate. You calculate all possible components with this algorithm. Whereas in DFT, as I was showing, I could have calculated first row, second row separately and say, okay, I only need to calculate first and last rows, and I don't want to calculate anything in between. With FFT, it's not going to work. It's going to calculate all 8 of them, but faster. Yes, so maybe it's still going to be worth it. Yes. So how exactly then that works? Before that, let's see actually how the efficiency increases for FFT relative to DFT. So if you have 256 samples, now your relative efficiency is 64 times less multiplications. If you have 4096 samples to calculate, then your efficiency is increasing all the way up to 683 to 1. Yes, that's how many times less multiplications you are going to need. So actually, the bigger is your FFT sample size, yes, the more benefit you will have from moving from DFT to FFT. So how exactly that works? Let's check time. So that works basically by splitting your samples into groups of 2 samples, because for 2 samples, if n is equal to, then FFT and DFT are equally efficient. Well, that's the minimum number of samples you need. And accordingly, there is no possible any improvement. So you split all your samples into into groups by 2 and apply DFT, discrete Fourier transform, for these groups. Now, each of these base functions is called a butterfly because its graph actually looks like a butterfly, resembles, yes? And then the idea is quite simple. Now you merge 2 sampled DFTs into 1 4-sampled DFTs. So from 2 samples and 2 samples, you create 4 samples. For 4 samples and 4 samples, you create 8 samples. From 8 and 8, you create 16 samples, and so forth. Yes, so with each next stage, stage 1, stage 2, stage 3, you merge previous stage results into higher number of groups by running the same butterfly operation again and again and again. So, conceptually, that butterfly base operation looks like that. Yes, so if you rotate it, you will see this butterfly. And what it does, it calculates summation and difference between input A and B, where input B is multiplied with some coefficient W. Yes, so B is multiplied by W plus A, that is this sample, minus this is this sample. Yes, whereas W coefficient is none other than this complex exponential we've been speaking about, which can be represented as cosines and sines if you want to, yes, but other than that, it's still the same as the power of R. That's also quite important, yes, because exponential is in that case is providing additional benefits. So let's say if we speak, you have exponential of minus j 2p versus n, and you square it, then you would have 2 multiplied by 2p versus n. So essentially that means that this rk is none other than this n multiplied by k, which we had. So now it goes into the power indicator of this exponential. So this coefficient can be calculated as a single number, and then you simply take it in the first power, in the second power, in the third power, and so on and so on. So once you have calculated these, 4 of them, let's say we have 8 samples, so that means you split 8 samples into 4 groups by 2. Yes? You calculate each of them with this base function of butterfly, here, 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 and so forth. And then start merging them. So you take 2 groups of 2 samples and merge them into these 4 samples by running the same butterfly like so and like so. The same goes for this group. Once you're done with that, you start merging the groups of 4 into groups of 8. Yes? So again, you take 1 sample from the first group, 1 sample from the second group, and calculate this base operation of butterfly. Then you take the second sample of the first group, the second sample of the second group, and calculate the butterfly. Then, as you imagine, third samples, and the last ones are fourth samples. And this process can continue further. You can group then 8 samples into 16 samples, and 16 into 32, and so on. So this makes sense now why it has to be a power of 2, because if there was just like any extra sample or extra 2 samples, you would simply have no other samples to group it all the way to create another 8 samples group. Yes, so you have to have 8 more to be able to do so, which will bring you to number 16. Now, if you will try to merge them by 16, then you will have to go to 32 at least, or maybe even 64, and so forth and so forth. So that automatically happens from here. There is one detail here, which I will also mention, is that inputs are not in the correct order. Yes, this is called, wait, how it was called? Reversive order. Yes, reversive order means that you take 0, convert it into a binary, and read it in reverse. So 0 remains 0. Then you take 1, convert it into binary, read it in reverse, and it becomes 4. Yes, so that's as simple as that. You simply take a reversive order of these numbers, and the outputs are in the standard order. Now, the same procedure can be represented in graph form like this. So now that is the algorithm you can program, actually. Yes? Now, that is the whole idea, which runs in stages like for loops. Here you have a stage. Inside of each stage, you have a block. Inside of each block, you have a pair. So essentially, that means you can nest for loops 3 times for stage, for block, and for pair. And inside of each of these pair, you will calculate a product, just one product, one product, one product, one product, one product. So that is 4 products. Here you will also calculate 2 products and 2 products, again 4 products. And here you will calculate 4 products with 4 different coefficients. So that totals to 12 multiplications of which we spoke about, contrary to having to calculate 64 standard discrete Fourier transform coefficients. Okay, with that in mind, that algorithm can actually be implemented in one of our course projects. I actually give students task to do this one, but it's never going to be as efficient as FFTV, which is used in MATLAB, for example, or can be downloaded and used for free, FFTV version 3, for example, which of course uses multi-core systems, advanced methods when you do not have power of 2, and all that stuff. So this MIT product, MIT open source, I believe open source or open use, not sure exactly, license, but that's mainly used in MATLAB, for example, in Octave as well, in Python, as compiled C module to run this FFT transform. So you can program this one as well. It's not going to be as good as MIT's, probably at the first step, but you can improve it further, yes? So that's the idea. Now, about these coefficients, why there are so few of them, like 0, um, 2, 1, and 3, and all that's all. Well, again, that's because, as we discussed, there are actually not so much of unique numbers and their combinations, like 0.7, 0.7, 1, and -1, and so on. So that gives you 4 different coefficients, real part and imaginary part. Because they start to replicate, yes, each other. For example, there are 2 properties, symmetry and periodicity, yes? So probably at this step it's going to be even easier just to show that in demonstration. Format along and say I will have this coefficient as that would be JP double P divided by N. Yes, so let's mark it like that. W is a complex exponential minus 1i multiplied by 2p versus 8. That is a complex number. Yes? Well, actually, let me make this format short. Maybe E. Maybe it will look better. I suppose, yes, it will look better. Probably this way. So what I'm going to do now is to take this and essentially, if we check this table, that W coefficient we now have needs to go all the degrees, well, maybe not exactly all of them, but minimum degree is 0 by 0. Maximum degree it can go up to is 49. Yes? So when you have 7 by 7. So that means now we need to calculate 50 degrees of that coefficient and see what happens to that coefficient. That's exactly what I'm going to do. W will be element-wise powered into degrees from 0 to 49 included. And I want it to have to be column-wise. So here you have 50 coefficients calculated. Now we have 2 properties here actually. One is periodicity and one is symmetry. So what is about it? So let's say we consider having 8 of these coefficients. So that's 4, 5, 6, 7, 8. What you will notice is that actually this coefficient here and this coefficient here are opposite. So this has plus sign, minus sign, and this has minus sign and plus sign. So they are numerically the same, but the signs are different. Same actually goes for this one. Yes, it was plus and plus. Now it is minus and minus. So essentially that means we actually have 4 of them different only, and all the others are replicas with opposite sign. And if we check even further, then these 8 are going to be exactly the same as this 8. So there are in total only 4 unique values, and all the others are variants with different sizes, and well, or they are exactly the same at all. So that's why we have to calculate only 3 coefficients. W at the power of 0, even a complex number, if you calculate it at the power of 0, is just 1, which is the first one. And there are now 3 other coefficients, W power 1, W power 2, W power 3. Because W power 4 is now the same as minus W power 0. W8 is the same as W0, W4, or W0, sorry. So with that in mind, these unique products, these unique multiplications are much less. And that's how it works, yes? Now, finally, the very short video of the signal processing, yes, when this actually is so fast enough that you can run it in this small microprocessor, microcontroller. I'm not sure exactly what they use. Something again about the advertisement. Skip. Yeah, so you send some signal, and in real time, it shows how spectrum of your signal changes for your signal. Yeah, so a measure of signal. That's actually a spectrum analyzer. Now what it happened here, there is a small switch that allows you to change the number of samples. So n is 8 or 16 or 256 to increase the resolution. Yeah, so basically it works in real time. Yeah, so it collects data, converts it into numbers, runs these numbers for FFT algorithm, and displays that on screen. And that is so fast that it actually follows to the signal. Yes, so that's how spectrum analyzers work. And of course, you can implement this fast Fourier transform for other purposes as well. So, okay, that is going to conclude today's class. We will finish shorter as well. And on Wednesday, we will try to do some stuff with that. Yes, and see some discrete signals to do some practical exercise. So thank you then for attention. See you on this Wednesday. If you have any questions, you can always make email. And well, yes, thank you.